Advanced Algebra 2 students, welcome to your 3.3 notes, and yes, they're labeled wrong, sorry. Linear programming. Linear programming is kind of the capstone activity for this chapter. If you know how to do graphing lines, if you know how to graph inequalities, if you know how to find intersections, you are going to do great on this topic. We only add in one new thing basically. So we'll look at that. So linear programming is a method of finding a max or minimum value of a function that satisfies a set of conditions we call constraints. Constraints is just a fancy name for the inequalities. And anywhere that we would find like basically the solution to a set of inequalities or a system of inequalities, we call the feasible region. So, a little new terminology: constraint, feasible region, but we used to know those as inequalities, and solution, no big deal. All right, most of the time with linear programming, you're going to want to do more than just identify, though. You want to find the best combination of values that would allow you to minimize or maximize. And that function that you're minimizing or maximizing is called the objective function. And it can have a min, a max, neither or both, depending on that feasible region. All right, so here are some examples. A lot of the problems we look at with linear programming look like this, where you have like a bounded region. So in that case, we would have both a min and a max. At times, though, you have unbounded, and so in these situations, you'll have either a max or a min, but not both. Now, when we talk about having a max or a min, we're talking about for the objective function, and you can see the vertex principle is kind of cool. We're not going to worry about the math involved with it, but essentially it says if there's a min or a max, it occurs at one of the vertices. So essentially our job is find the vertices, apply the objective function. All right, so let's start with the problem that you see here. We're going to go ahead and graph the system, which we're calling constraints. X greater than or equal to 0 just means that we're over here, okay? All right, we need to graph the next one. Y is greater than or equal to 1.5. Oh, okay, so here's the deal. You notice how our axes aren't labeled? Let's go and figure out how we want to label them. So I'm going to do this. I'm going to start by finding intercepts. So I'm going to start with this one right here. I know that if x is 0, then y would be 4. I know that if y is 0, then x would have to be 8. Okay? I need these values to be able to label things accurately. Okay, so here we go, 3x plus 2y. That means if x is 0, y is 6. And if y is 0, then x would be 4. So what I'm seeing here is that the largest x value that I run into is 8. The largest y value is 6. And quick count here tells me I have at least about 10 spaces. So I'm going to think counting by counting by ones is good to go on this. I'm only going to label every other one, but I'm just going to count one box equals one space. All right, let's graph. I'm going to come back to this one. I said I wanted to start with that one. I changed my mind. 8, 0, 0, 4, and I need to connect. You notice it says that we're talking about less than or equal to. So we're going to have to shade below that line. Again, we'll deal with the shading later. Our next one, we're going to go to the last one, 3x plus 2y less than or equal to 6. And I'm going to mark my key points here, my intercepts. And they look like that. And again, those need to be connected. And the connection would look something like that. Now that one's also shaded below. So right now we're just down here in this, well, it's a quadrilateral. It has 4 sides. There's one that I skipped over though. Remember, y equals 1.5. So I'm going to need to sketch that one. That graph would look something like that. I was off just a hair. I'm going to try to clean it up just a bit. And so our feasible region is right here. This region right here. Now, our next step, so that's basically just graphing inequalities, right? We've done this before. But this is what's new. We need to make sure we find the vertices of our feasible region. I'm going to suggest that 3 of the 4 are pretty simple. 0, 1.5. Well, maybe I'm changing my mind. Maybe only 2 of them are really simple. 0 and 4 is pretty simple. Now this one right here, you got to be careful, but when I look at that, it very much looks to be at 2 and 3. But before I have too much confidence with that, I want to go ahead and test it. So I'm talking about the blue and the green, right? So if I check 2 and 3, that gives me 5 plus 15. That works. 2 and 3, 6 plus 6 is 12. That works too. I know I did that math kind of fast, but essentially I'm just plugging in 2 comma 3 here and here to see that it works. This one right here isn't so bad, but it's not just a gimme. What I do know is the y value is 1.5, and I'm going to have to plug that in to this equation to the line that I've got blue so that I can find this vertex. And when I plug in 1.5 for y here, that gives me an x value of 3. All right, so here is the new thing. We have to list our vertices. We found all of them. Let's list them. And then we're going to apply the objective function. Now this was written up here in the instruction, so it's p equals 25x plus 30y. And we're going to get those values. So there's no particular order, I should say, for how we list our vertices. We just need to make sure we list all of them. So if you have 4, list 4. Sometimes some of the vertices are even, 0, 0 or points like that. They still need to be listed. All right, so if I plug in 0 for x and 4 for y, we get 120. If I plug in 2 for x, that's 50. 3 for y gives me 90, so 50 plus 90 is 140. 3 times 25 is 75. Add in 45 and I'd get 120. And then 0, 1.5 would give me 45. All right, so the question then becomes, well, what do I do with this information? Well, and honestly, it kind of makes more sense when it's a business application than when it's just a random problem like this. But here's the key word: maximize. What that means is I'm looking for the maximum value, and I look at the objective function and I see that 140 is the highest value. So the max value of 140 occurs at 2, 3. All right, it's kind of weird when they're just throwing random inequalities and objective function at you. So don't worry, we will look at real application problems. That's up next, actually. All right, here we go, a real life application problem. I'm going to let you guys read this. So if you haven't read it yet, if you need to pause the video to read, do it now. But I'm going to move on. So my first step is to define variables. And I'm going to say, well, what is it that we're going to end up trying to find? Well, we're going to try to find the number of advanced players. So I'm going to label that as X. We're also going to be looking for the number of intermediate players. Now here's the part that that's new, I guess I should say. It's brand new to this. When we do linear programming, we're always trying to find, like, what is it that we're trying to maximize or minimize. So I see right here it says to maximize the number of players. So my objective function, number of players, I'm just going to say P equals, well, number of players would just simply be X plus Y, number of advanced plus number of intermediate. But now we need to start looking at the constraints, okay? One constraint, we have cost restraint, and we know it's $75 for an advanced player and $50 for an intermediate, and we can spend no more than $13,250. Okay, you have to be careful on the next one. Sue must send at least 60 more advanced than intermediate players. So if I take the number of advanced and I subtract the number of intermediate, that number better be at least 60. Sometimes those can be confusing. You might need to read it 2 or 3 or 10 times just to make sure you have it right. But it says very clearly that Sue has to send at least 60 more advanced than intermediate. So advanced minus intermediate better be at least 60. And a minimum of 80 advanced players. Well, that's a pretty straightforward equation. X is at least 80. All right, and I think we have all the constraints. Oh, we almost left out one. We better well, we already know that x has to be more than 0. I would argue there's one we need to add in there, and that is that y is greater than 0. We're not going to send negative intermediate players. And you may have caught this when I wrote it, but I left off a variable down here. There's a y right there. I think I said it and didn't write it. All right, our first job is to figure out how do we want to label this graph. And to do that, we need to figure out what the graph is going to look like. So here we go. If x is 0, then our y value here would be 265. Okay, well, we're not going to be counting by ones. I kind of know that right now. If our y value is 0, then x is 13,250 divided by 75. I'm having to punch that in the calculator right now. And it's 176 and 2/3 players. Ooh, feel sorry for that last one. Okay, so essentially I can see I have some knowledge now on intercepts, but let's check the others. Now this is an interesting one. If x is 0, y would be negative 60. How am I going to do that? Well, we're going to have to be creative on the way we graph that second equation. The third and fourth, I'm convinced, are pretty straightforward. Let's talk about labels. All right, I know I need my x values to go to at least, y values 265. I have somewhere around 11 spaces here, I think. So how about if I count by 25s? Is that going to be enough? So that would be 50, then 100, 150. Oh, I think I'm going to get it just barely. 200, 250. Yeah, okay. And if I'd mess that up, I'd have to just try it again, right? That happens sometimes. And I'm going to label the x-axis the same way. That would be 50 right there. 150. And I'll go ahead and mark 200. We're not going to go past that on the x-axis. All right. Let's graph all the easy stuff first. We'll come back to that second equation afterwards. So 0 and 265, I'm going to approximate. It's about there. 176, it's about there. Again, just we're trying to approximate. We don't need exact lines. We just need a good idea. So the blue one, the 75x plus 50y looks like that. And based on the inequality, I can tell you we're shading below. We'll come back to that detail later, though. All right, the next one, x greater than equal to 80. Very simple. Vertical line somewhere right around there. So now we're down to this triangle region right here. Y greater than 0 tells me I have to be above the axis. So if you wanted to graph it, you could. It's kind of already graphed as the axis. Keeps us in that triangle. All right, let's talk about the one that we skipped. All right, I know 1 point, right? 60, 0. I mean, technically you could say I know 2 points. The problem with the other points, or the other point, is that it's off our grid. So I would have had to change the way I labeled these axes in order to use intercepts. So in a situation like that, sometimes it's worth kind of thinking outside the box a bit and saying, all right, so my idea of graphing by intercepts wasn't maybe the best, but here's what I could do. I could think of it as, I know it's y equals x minus 60. Again, I'm ignoring inequality here, but just thinking of it in terms of a line. So if I add y and subtract 60, I'd have this. All right, so we already knew that y-intercept was the one we didn't want to have to mess with, but you can see that the slope is 1. Now this is going to be a little rough because I'm essentially just approximating. But again, what we're looking for in this kind of situation is a good approximation. So if I do something like this, I can probably get a line that's decent. Can I trust the exact values that we intercept with? No, no, no. but it will serve as a good visual aid for us. All right, let's talk about where we're shading here. Now this can be a little tricky because we know we're under the blue line. We have to be real careful with this green one, and it's easy to make a mistake here, so don't fall into this trap. This says it's greater than, so you might be tempted to say, oh, we're shading above, but when you're in standard form, you can't trust that. You got to test points. 0 minus 0, is that more than 60? No, this is not shaded. This is actually shaded underneath. So our shaded region is this quadrilateral right here. It might be easy to miss. That green line is the challenge on this problem. But be careful with it and you can handle it. So we have 4 points of intersection right there, and then we have 2 of them over here. One is right here at the axis. That's actually a pretty easy one to find, isn't it? 80 comma 0, and then we have another one right there. As a matter of fact, I think we have a couple of these that are pretty simple to find. One of them is like 176.7 comma 0. You know, for realistic purposes, since 2/3 of the kids aren't going to take that trip, I'm going to go ahead and just call it 176 now. But we have 2 more points we need to find. I would say this one right here wouldn't be too bad. We just need to plug in 80 for x, and so if I go back here, 80 minus y is equal to 60. We know that it's got to be 20, so that one's 80 and 20. All right, so the real challenge one here is this last point of intersection. You can't just approximate that thing. What you have to do is you have to solve the system, basically. Now, here's my advice. Graph these on your calculator. Now, I've already done that, and I found the solution, the intersection, to be at the point 130 and 70. Why don't you, though, if you need to, pause the video and graph it. Now, if you want to use Desmos, you can type it in like this. If you use your TI-84, you have to go ahead and solve both for y. But either way, you can graph this and find that intersection. It's 130 and 70. Okay, now remember, we have one job left. We need to go ahead and list the vertices, and then we have to do our objective function, which was a simple one, just number of players. P is equal to x plus y. And let's see what we come up with. Basically, again, very simple objective function. 130 and 70 was an ordered pair. 176 and 0. 80 and 0. And then I can't hardly read my own writing, but I believe that other one was 80 and 20. All right, so the objective function, just basic addition. And we have to make sure we know, what are we trying to do? Well, we're trying to maximize the number of players, and I see that right here. So let's make sure we answer the question correctly. Find the number of each type of player. Well, this is 130 of the advanced players, and 70 intermediate players. And it's to camp, right? To soccer camp. All right, so there's a little work involved with these, but it allows us to be more efficient with our businesses or with our money. It's kind of a cool thing to be efficient with. All right, we have 2 left, and I'm already over time. So in order to maintain your sanity and to respect your time, what I'm going to do is actually just go through and work through these next 2, and I'll post the answers on this video. So what I'd like you to do, though, is try to work through both of them, and then after you've given it a shot, take a look at mine. If you need to copy some things down, do that, but take a look at it, and I'll do some quick talk through it as well to explain what's going on. But again, go ahead and pause the video now. All right, I'm really hoping you paused and gave this a shot. I know it's a challenge. Here's the biggest thing with these type of problems. Finding the objective function is really important. So when I looked at the one with the bookstore manager, I had to know right away they're trying to minimize costs, which means my objective function is C equals, well, it's 200 times the number of bookcase A's plus 125 times the number of bookcase B. That's the bottom line here. We got to minimize cost. That is not part of the constraints. That's simply the objective function. Now you can see the equations I came up with here. You can see the feasible region, and we had these vertices to deal with. We had 3 of them. And you can see it was fairly close between 8 and 4 and 4 and 12, a couple $100 difference, but 8 and 4 was a slightly better option that would still allow for the correct number of, well, the correct amount of bookcase space, but not go over budget. Okay, let's look at the next one. This one, picking the constraints out might have been a bit of an issue. You were, again, maximizing profits, so 30x plus 50y. But to get the inequalities, you had to look at it in terms of factory A, where we had 2 work hours and 4 work hours, and we could work for at most 10. That's this blue equation. And then factory B, the acoustic was 4 work hours, the electric was 3, so 4x plus 3y has to be less than or equal to 10. That's a little tougher to pick out, I get that, but you're capable, okay? Again, we know how much money they make on each type of guitar. That's our function here. And you can see I also put the laws of nature in. We're not going to have negative guitars. One thing that I had to debate when I made this when I was working through this problem was, can you have 2.5 guitars? You know, we have 2 points that are 2.5, 0, and then 0, 2.5. And I would argue in this kind of a situation, the answer is yes, because essentially we're talking about in one day, right? So why couldn't they stop in the middle, and then over 2 days we could have 5 guitars here or 5 here in 2 days? So I would argue that that's okay. There are some situations, you know, kids going to soccer camp where it's not good to have 2.5, but for guitars we can do half the job and then pick it up tomorrow. All right, so but even with that being said, where the profits were maximized was with 1 acoustic and 2 electric. You can see the work there. And yeah, so guys, these are problems that put together everything we've done in this chapter, and a little bit even prior to that with linear equations. If you can do these, I'm convinced you can handle anything I'm going to throw at you on your test that's coming up. So please make sure you work hard to understand this. Ask lots of questions. Look at other examples in your textbook if you need to, but make sure you figure out what you need to do to get these done. Hey folks, thanks for sticking with me, and we'll see you in class.